Hello and welcome to our long-awaited webinar, where we can finally present you our latest innovation in the field of protection devices. We are thrilled to welcome you to our webinar as we set out to explore the remarkable features and applications of this state-of-the-art protection device. In the course of this webinar, we will look at the motivators to develop a universal device with connection inputs for LPITs. But of course, the focus will also be on the functions and innovations of the SIPROTEC 7SY82, as well as possible applications and changes in the interaction with the protection devices. But this webinar isn't just about technology and features, it's also about collaboration and knowledge sharing. We therefore encourage you to take an active part in this session. You can do this directly in your browser next to the video. Ask your questions and let us know if the LPIT technology can be beneficial for you. My name is Lars Schulz. I am product manager for our Universal SIPROTEC protection devices, including, of course, the 7SY82. I'm very pleased to be your host today and to be able to count also on the support of my esteemed colleague, Bruno Arras. Welcome, Bruno. Please introduce yourself to our viewers.
Thank you, Lars. Introducing myself, my name is Bruno Arras. I'm portfolio consulting professional for SIPROTEC device. It's a great pleasure to be here today presenting this webinar with you.
Thanks, Bruno. But before we begin, a few organizational tips. The webinar will be recorded and can be watched again using the same link. The handout will be available for download here in the system towards the end of the webinar. At the top right of the screen, you will find the field Ask the Speakers a Question. You can use this field to ask us questions about the content. Your questions will be answered during the webinar or afterwards via email. And now that we have sorted out all the organizational things, let's start with a brief explanation of terms. We will use the abbreviation LPIT more frequently during this webinar. This stands for Low Power Instrument Transformers. These are sensors that enable current and voltage measurement through alternative technologies. Now the question certainly arises as to why these sensors, or LPITs, should be supported by protection devices. There are actually a number of reasons for this. First of all, there is the small size and weight of the sensors compared to conventional current and voltage transformers. The use not only reduces the weight of the switchgear, but also ensures a lower use of materials and thus also lower emissions and a lower ecological footprint. As the name indicates, another significant difference lies in the level of the output signals. Both signals for current and voltage measurement are small secondary voltages that are processed by measuring or protection devices. They are so small that they can even be transmitted to the device on a cable terminated with an RJ45 connector. This results in increased safety for the operating personnel, as well as faster and easier wiring and commissioning. Furthermore, the Rogowski coil in particular can be used for a significantly larger operating range, thus reducing the variance in the transmission ratios and increasing flexibility as the nominal operating current can now be changed during the life cycle of a switchgear. So there are a lot of potential advantages coming with the LPIT technology that makes them quite attractive for the use in medium voltage. Those of you who have been familiar with our protection and automation folio for some time will know that the topic has had a place in our portfolio already in the past. The first developments even began in the previous SIPROTEC 5 generation. At that time, the 7SJ65 was a full-fledged SIPROTEC 4 protection device, and the 7SJ81 was a compact SIPROTEC 4 protection device, both for the connection to low-power instrument transformers. Until today, the sensors used have always been external products and were based on the principle of an inductive small signal sensor for current measurement and a resistive divider for voltage measurement. But now, our colleagues from medium voltage have also developed their own solution for air and gas insulated switchgears, both of which are based on the Rogowski coil for current measurement and a capacitive or resistive divider for voltage measurement. And naturally, it was our aim to offer a high-performance protection device for these solutions on our current SIPROTEC 5 platform. We have now succeeded doing this with the 7SY82. And this is, of course, only the first step of the development, which will be continued with a modular device and an extension modules for the platform. In addition, our colleagues from medium voltage also want to offer these sensor solutions for their entire portfolio. But Bruno will now explain exactly what the SIPROTEC 7SY82 is all about and what features, functions, and capabilities this device can offer you. So Bruno, stage is yours.
Thank you, Lars. Then I take over to introduce you to the main features of the 7SY82. As we have just heard, the 7SY82 is the equivalent to the 7SX82, which allows the connections of LPITs. Thus, the basic properties are also largely the same. This means that the 7SY82 is a universal device. In other words, a digital protection device in which you define not only the usual additional functions, but also all the main protection function as part of the configuration. We therefore speak of a multifunctional protection device. As you know, from the SIPROTEC 5 device, this is suitable for all types of networks, regardless of whether the neutral point is grounded, compensated, or isolated. As you can see in the photo on the back of the device, there are 2 installation slots available for plug-in models, but this can currently only be used for communication models. This is actually nothing new so far. What most people may not know yet, although this is now also available with the 7SX82, is the function point dependent use of the display size. The 7SX82 and the 7SY82 only come with a large display. In the parameter set, you can set whether the area of the small display or the entire large display is used. For the large option, function points are due. On the one hand, this reduces the number of variants in production, and on the other hand, to have different display price of the device. There is also a slight difference to the 7SX82 in the 2 available hardware variants. While the connections for the 8 LPITs can still be equated with 4 times current and 4 times voltage, the number of binary inputs is reduced by 2 binary inputs for the both variants. This was necessary in order to exclude any influence on the nearby LPIT inputs. With this, it is possible to reach a conclusion. The 7SY82 is a complete member of the SIPROTEC 5 family. Like the 7SX82, the 7SY82 is a non-modular SIPROTEC 5 device, whose main area of applications is medium voltage. As a universal device, it covers the functional scope of the following type-specific device. The 2 overcurrent protection device, 7SJ81 and 7SJ82 of the SIPROTEC 5 series, which also contain capacitor bank protection functions. The distance protection 7SA82, the line differential protection 7SD82, and the 7SL82, in which the latter 2 main protection functions can be used in parallel. And last but not least, the motor protection 7SK82. Unfortunately, we have not been able to provide the complete planned range of functions with version 9.60, which was released at the end of August 2023. So that currently only the function shows on the following slides are available, but this represents a large part of the functionalities of the universal device. The further functionality will be introduced into the 7SY82 with the next major release. With the version 9.60, were released the non-directional and directional functions for phase and earth faults, voltage and frequency protection, power directional protection, breaker failure protection, as well as KU protection are also available. In addition, other functions not explicitly mentioned here are available. You can see the exact scope, for example, in the function point calculator in the SIPROTEC 5 online configurator. With the next version planned for November or December of 2023, distance protection, synchro check, and automatic reclosing, to name just a few highlights, are planned, among other things. In the following major version, around April 2024, many more functions will be added to map the functional scope of the 7SX82 to the 7SY82. I would just like to mention the line differential protection function as the main protection function. From then on, the 7SY82 also supports the remaining plugin models for the acquisition of analog mesh values or for arc protection. In addition, there will then also be a variant for the 7SY82 for detecting 12 thermal sensors, as available in the 7SK82, the motor protection relay. If you look at the 7SY82 from the back, you will notice the 4 RJ45 sockets at the point where the current terminal block used to sit to connect conventional current transformers. These RJ45 sockets are used to connect the non-conventional current and voltage sensors. These LPITs inputs are standardized according to IC 61869-10 and -11. This means that all sensors compatible with this standard, whose connection cables end in RJ45 plugs, can be connected and used together with the 7SY82. These two can be described as universal. But which LPITs can be used now? What measurement principles do these compatible sensors support? The current sensors use either the Rogowski coil or low-power iron core coils. The voltage measurement is carried out either via resistive or capacitive dividers. Of course, the selection is stored in DXY5, so that the appropriate sensor type is set as part of the parameterization. Lars, now can you tell us more in deep details about the LPIT inputs and the sensors?
Thanks, Bruno. Most definitely.
Let us take a closer look at the measurement inputs of the I/O module. Like all modules in the SIPROTEC 5 platform, this one also has its own identifier and is listed under the name IO141. As can be seen in the other pictures, the sensors are connected to the protection device by means of an RJ45 plug. This type of connection is explicitly described as an option in the sensor standards. The table in the middle shows the assignment of the measurement signals to the individual pin of the connector. LPCT is here an abbreviation for the current sensor, LPVT for the voltage sensor. In addition, it can be seen here that on the pins with the numbers 3 and 6, connections are used for a temperature measurement. This can be utilized for capacitive voltage dividers to achieve even higher accuracy. The very good measurement accuracy, which is in the same order of magnitude with class 0.2 as our non-modular SIPROTEC 5 protection devices with conventional measuring inputs, should also be clearly emphasized. The LPIT measurement inputs A1 to A3 are intended for the use of the current and voltage signals of the individual phases, and the fourth input for a sum current sensor and/or an additional voltage sensor. As mentioned earlier, the standard allows the use of an RJ45 cable, but limits the maximum permissible cable length to 10 meters. While this surely is a limitation, the advantages of this type of connector outweigh the disadvantages, and 10 meters should also be more than sufficient for most of the medium voltage applications. Now we have talked very intensively about the hardware, but what about the connected signals? which nominal values are supported by the device. To explain this, we need to take a quick look at the world of conventional transformers. In the world of conventional current transformers, for example, it had always been the case that a suitable transformer had to be selected for each application, for each primary nominal current of the system. These have always converted the primary current to 1 amp or 5 amp secondary current. This standardization has made it possible for protection devices to be connected to basically any current transformer and always operate in the same measuring range. If a higher current was to be measured, the transformer was selected accordingly. The major advantage of the sensor technology should be the wide working range and the associated lower variance in transformation ratios. This means that a Rogowski coil can be used for a wide range of nominal primary currents. What this circumstance means for the protection device is shown in the following graphic. As we can see, at the same different primary currents, we reach different secondary so-called nominal values. In order to map this dynamic range, the 7SY82 must be able to work with a range of secondary nominal values. This is made possible by the fact that several measuring ranges are now realized in the device hardware instead of one. And these are selected depending on the sensor and nominal values in order to meet the accuracy requirements. This now makes it not only possible to use the same Rogowski coil for different nominal currents, but also sensors from other manufacturers with maybe different ratios. Of course, these properties apply not only to Rogowski coils, but to all sensor principles mentioned by Bruno. All these aspects now ensure that with the IO141, we have succeeded in creating a universal input for use with all sensor types from different manufacturers. Of course, it is essential that the sensors have been manufactured in accordance with the IEC 61869. And our goal is to be able to offer all users compatibility with as many sensors from as many manufacturers as possible. In order to be able to actively recommend LPITs, it is of course necessary to carry out detailed tests, preferably together with the manufacturers. By the time the 7SY82 was officially released last month, we had been able to test the sensor portfolio with our own solutions for air and gas insulated switchgears, and additionally with 2 established sensor manufacturers. These external tests have taken place in the laboratories of the sensor manufacturers with very satisfactory results. These investigations have already confirmed our assumption that when protection devices and sensor technologies are developed in accordance with the standard, compatibility across a wide range of manufacturers, let it be protection or sensor manufacturers, is not only a marketing argument, but measurable reality. In order to show exactly which applications are possible with the 7SY82 and how the connection of sensors to the device can look like in different cases, I would like to hand over to Bruno again.
Thank you, Lars.
Thanks, Bruno.
Now, let's take a look at 3 examples. Case 1 is, of course, our favorite as a CME solution. You opt for a CME switchgear with CME sensors. That means the SI bushing. In this case, you will receive precisely coordinated measurement technology, whether in air or gas insulated switchgear. The installation takes place in our switchgear plants, and you benefit from the advantages of the Rogowski coil in current measurement. Of course, the sensors are suitable for all protection principles. The correction factors of the CME sensors are stored in the database and are therefore available in DIGSI. Lars will explain more about this later. In this application, you will receive the know-how from a single source, a convenient solution made by Siemens. Now, let's look at case 2. If you prefer a switchgear from another manufacturer, and perhaps the sensors are already fixed and are not supplied by Siemens, we are still completely flexible with the 7SY82, as long as the sensors comply with the IC standard, and thus their RJ45 connectors are compatible with the reverse inputs of the 7SY82. I had already mentioned the supported measurement principles of the LPITs. You also know by now that, if at all possible, we also make the correction factors of non-Siemens sensors available in the database, and that this can therefore be easily inserted into the settings. So we can say the 7SY82 adapts to your application. As at the last example, let's look at case number 3. If you have a switchgear from another manufacturer, if you want to use our 7SY82 but have not yet specified the sensors, then just contact us. We are happy to support you in selecting the right standard compliant sensors. We then also try to include them in the sensor database if they are not already included. Let's move on the connection examples. That means how the different sensors are connected to the 7SY82 and what other options are available. On this slide, we see the simplest solution. When using combination sensors to detect phase current and conductors to earth voltage, they can be connected directly to RJ45 sockets A1 to A3. If a separated sensor is used to detect the earth current, you can be plugged into A4. It gets a bit more complicated when separated sensors are used to measure current and voltage, since each of these sensors has its own RJ45 connectors. For this, we recommend the adapter box shown here on the slide. In the top 2 rows are the connectors for 8 LPITs. The current sensors are plugged in the first line, and the voltage sensors in the second line. The third line then provides 4 outlets, which are connected to the inputs A1 to A4 for the 7SY82. In this way, the 3 current and voltage signals are of each phase, as well as the signals of the earth current and the possible 4 voltage in the 4th column are each combined on a connecting line. In addition, the adapter box also supports testing the 7SY82 by providing the connections for coupling test signals in the 4th line. If you look closely, you will also see in this example that the combination transformers of the 3 phases, as well as the separated earth current sensors, all of which could also be connected directly to the device, are connected to the first line of the adapter box. Thus, to test the 7SY82, the supply lines of the sensors would not have to be disconnected from the device, and the supply lines of the test device would have to be plugged into the device. In brief, the test device used the 4th line of the adapter box to couple the test signals without having to touch the connections of the sensors to the box, or the connection from the box to the protection device for testing. This makes testing the 7SY82 very easy. Now, on the slide we see basically the same as on the previous one, except that here no combination sensors, but separate LPITs for current and for voltage measurement are connected to the adapter box, which means that, at least when the test device is connected, all 4 lines of the box are used. So now I will hand over to the floor again to Lars, who is already eager to show you how to make the configuration of the sensor in Dixie.
Thanks, Bruno.
Welcome.
It is also important to mention that the device can, of course, also be tested without the test and adapter box by connecting the test equipment directly to the protection device. Now I would like to talk about what is probably the most important step before the protection test, the settings in Dixie. A new measurement technology and a new input module in the 7SY82 understandably require changes in the workflow. Our highest priority was to keep the additional effort as low as possible. Nevertheless, there are two significant changes which I would like to briefly describe now. The first change is related to the setting mode. The protection parameters in DIXI 5 can always be entered in primary, secondary, and percentage mode. What changes in the 7SY82 can be explained with a short example. Let's just assume an outgoing bay in which a really simple non-directional overcurrent protection function has to be set. The nominal current of the field is, let's say, 500 amps. A conventional current transformer with a ratio of 500 amps to 1 amp is installed. And the threshold for the trigger for stage 1 should be set for a value of 700 amps with a delay of 200 milliseconds. In DIXI, the following settings would be made. For primary, the values could simply be adopted. Threshold 700 amps, trip delay time 0.2 seconds. For the mode secondary, our example would result in values of 1.4 amps and 0.2 seconds with the given current transformer. So far, so familiar. Now, SI bushing is to be used with the same requirements. It has a transmission ratio of 50 amps to 22.5 millivolts. For primary, we can use just the same settings as for the conventional example. For secondary mode, the whole thing gets now a bit more complicated. Should we continue to enter the threshold value in amps? Actually, it should be entered in millivolts since the sensor converts the primary current into a voltage. This would then result in a setting value of 315 millivolts for the SI bushing. However, if a current sensor from Celisco, for example, with a transmission ratio of 300 amps to 225 millivolts is to be used in the field, a different parameter would result. In this case, 525 millivolts. And based on these examples, it's really obvious that entering parameters in secondary values is difficult and therefore not recommended. Therefore, we have made the decision to hide these setting modes for the 7SY82. Therefore, protection parameters can only be set in primary or percentage values. The second change concerns the technical data of the sensor. There is a fundamental difference compared to conventional current and voltage transformers. The standard, especially IEC 61869-6, explains how to determine the accuracy class of low power passive current transformers by using a factor called CFI, where the I stands for current. This method is an improvement over the traditional approach of using the rated transformation ratio to define the accuracy class. The key advantage of using the CFI is that it allows for a higher accuracy class designation for passive LPCTs. In the past, accuracy class designation for conventional CTs was based solely on the rated transformation ratio. This created a challenge because individual transformers often had transformation ratios slightly different from the rated value. This variation in ratios lead to the need for a single accuracy class that could accommodate all transformers within the same class, resulting in an overall lower accuracy. With modern technology, we can now efficiently use the individual transformation ratio of passive LPCTs or LPVTs in protection devices. This is achieved by combining the ratio correction factor with the rated transformation ratio. We can clearly see the effects of these factors in the graphs displayed here. The figure on the left shows measurement errors of 5 randomly selected passive current sensors. In order to define all these sensors with the same accuracy class, class 1 would have to be chosen. If we now apply a corrected transformation ratio for each individual sensor, all sensors, the exact same sensors, meet class 0.1. It is precisely these correction factors for magnitude and phase that can be set individually for each sensor in the 7SY82. But now at first glance, this can seem like additional effort that we impose on our users. Now following, I would like to show you that this is not the case. The central components of this new workflow are our online sensor database, as well as the copy of it in your current Dixie installation. The database in the installation can be updated at any time with current sensor data. No permanent internet connection is required for this. The sensor data is then stored in JSON files in this database. In principle, a distinction must be made in Dixie between piece-specific and type-specific data. Piece-specific data, as the name suggests, is provided by the sensor manufacturer for each manufactured piece. Type-specific data is maintained and made available by us in the database. Depending on whether the respective manufacturer provides the piece-specific data, there are two ways of insert the correction factors. The first and easiest way is via the serial number of the switchgear panel. With this number, the complete data set of the sensors is found in the database and transferred into Dixie. No further adjustments of the sensor is necessary afterwards. The second way is via the nameplate of the sensor. If correction factors are specified for the sensor, then the manufacturer and type can be pre-selected in Dixie, and the correction factors are taken over from the nameplate, similar to what you see here on the picture, and all sensor parameters are set then. As soon as the sensor data is complete and the rest of the parameter set is complete, it can be transferred to the device. Let's take a look at the implementation of these points in the user interface in Dixie. First of all, the function block that is called LPIT IO141 is automatically added in each 7SY82. This is where the setting of the measurement inputs takes place. First of all, the type of sensor used must be assigned to the input groups. As described at the beginning, there is a choice between Rogowski coil and iron core coil for current measurement and resistive or capacitive divider for voltage measurement. After hardware synchronization has been completed, a sensor manufacturer can be selected. Here you will be able to select the manufacturers with whom we carried out successful compatibility tests and included them in our sensor database. This area is completed by selecting the desired sensor type. Depending on the type of data provision, there are now two ways to proceed. If the sensor data is provided by the manufacturer on a piece-specific basis, the year of the manufacturer and the serial number of the sensor set must be entered next. The software searches the database for the correct data set and automatically inserts all necessary sensor parameters. The values can then not be changed by the user afterwards. This is indicated here on the picture by the gray input fields in the correction factors. For current and voltage sensors, the work steps are identical in Dixie. The transmission of piece-specific sensor data to the database is currently only offered for the SI bushing of our colleagues in medium voltage. But of course, we strive to offer these possibilities for other manufacturers as well. Until then, the workflow for type-specific sensor data will be valid for all other sensor manufacturers. The only main difference is that instead of the serial number, the correction values for amplitude and phase must be transferred from the nameplate into Dixie. The transformation ratio is preset by the respective manufacturer by selecting the specific type, but can also be changed. The input mask looks basically the same. Of course, you can find more detailed information on all these parameters and the settings in our device manual. Once the sensor data has been set, all further steps do not differ in any way from a SIPROTEC 5 device with conventional measuring inputs, with the exception of the lack of secondary adjustment mode, of course. And with that, I would like to end this section and come to the summary and the key takeaways for you. With the 7SY82, you can open up a completely new measurement technology for your medium voltage switchgear. This sensor technology can generate decisive advantages for them in terms of design and operation. The universal inputs of our 7SY82 open up a wide portfolio of usable sensors, which are sure to include a solution for your switchgear. As you would expect from our universal devices, you will also benefit from the maximum possible flexibility during the entire lifetime of the device with the 7SY82. And we were able to prove our clearly formulated goal, a standard compliant measurement input for connection to all standard compliant sensors. Through the first tests, and we will continuously, of course, expand the portfolio of recommended sensors. And last but not least, as just shown, we have accommodated the new necessary work steps through intelligent extensions to Dixie without burdening the users with excessive additional work. And that's it from our side on our new 7SY82. If we have awakened your interest, please do not hesitate to contact us or your well-known Siemens partner, and we look forward to accompanying you on your new journey into this new technology. We thank you very much for your attention, and we will now take a look at the question asked. So let's see who asked some questions. Yeah, maybe we start at the bottom right.
Can you start? Are you ready?
Yeah, sure. We're ready.
So let's go to the first question. The list of protection applications does not include transformer differential protection. Are there plans to offer this protection function in the 7SY82 as well?
That's actually a pretty good question. That's totally right. It was not part of the list. And one main reason for this, which I also kind of explained earlier, is this limitation of the 10 meter of the cable to the device. The inputs, as it was mentioned, there are 8 universal LPIT inputs, so it would be also possible to connect 8 current sensors. But because of the length of 10 meters, we decided to include this one later when we also get process bus on our non-modular SIPROTEC 5 devices, including the 7SY82, which is planned for spring next year. And then we also plan to include transformer differential protection.
Okay, thank you, Lars.
Sure.
Let's see another question. Will there also be a modular 7SY85 or even a modular mixed device with the possibility of connecting conventional converters and LPITs?
Yes, short answer, yes, there will be. There was also visible on the roadmap. The 7SY82-85 will be a modular device with an LPIT module as a base module. But of course, also probably the IO241 will be available as an expansion module, which can be used with every SIPROTEC 5 modular device. Therefore, also mixed combinations are also possible.
Okay, thank you. Another question. I suspect that certain LPITs have built-in temperature sensors, and that's what the temperature inputs in the RJ45 jacks are for. Is this used to correct the measured value depending on the temperature, or is there a risk that the LPITs may become too hot?
I hope that I would pose a little bit on the manufacturer side, that they make sure that the sensors are not getting too hot or the switchgear is not getting too hot. But yes, the question was sort of already giving the answer that the temperature inputs are used for temperature compensation of the measurement, because for the capacitive divider, the capacitance is temperature dependent, and therefore, as it is pretty close to the hot spot, it's really necessary to also take this into account. But also the idea could be, because the temperature is then available in the protection device for maybe future updates, that this temperature can then also be used for some predictive maintenance features, for example. So would also be an idea maybe.
Okay, thank you.
Sure.
More one question. Will the line differential protection function of the 7SY82 also interact with the SIPROTEC 5 device with conventional inputs on the opposite side?
I would say the clear goal is yes, it should. But as I mentioned, or you mentioned it actually, that we have still to progress in the tests of verifying each of our protection algorithms for each function, that it works the same way for LPIT as for conventional transformers. This also needs to be checked. If there have to be adjustments made for a mixed, let's say, setup, where on one end of the line a conventional CT is, and on the other end the LPIT, it is planned that this also should be a possible solution.
Okay, thank you. Another question, why not having developed feature to read single wire memory in sensor?
There I have to say, maybe we have to move this question because I don't really understand what's it aiming at. Do you?
No, for me it's not so clear, but we can check.
Yeah, as we mentioned, we will answer all questions afterwards. So maybe we'll get back to this.
Okay, thank you. One question about arc flash protection. This function will be available in the 7SY82?
Unfortunately, not from the beginning. This is what you already mentioned earlier. We are not supporting any of the analog inputs, so no temperature measurement, no analog, let's say also plug-in modules, the NIE modules are not working yet, and therefore included is also the arc flash protection module. But this is a matter of a firmware update, and the plan is with the update coming in March, I guess it was, to enable all these analog inputs, and then also, of course, to offer arc flash protection. But again, this is not a hardware problem, just a firmware problem that will be solved.
And one question, I think that's related to that calculation that you make about the settings. Yeah. How did you get 315 and 525 millivolts?
Unfortunately, I don't have a whiteboard now where I can show it, but the idea was basically with the sensor rating of 50 amps to 22.5 to calculate with this ratio what secondary voltage do I get when I have a primary current of 700 amps. So I think you have to reverse the ratio and then calculate it by 700, and then you should end up with 350. Or 300 amps to 225 millivolts is the same way to reach the 525.
Okay, clear.
Do we have any more questions? Or?
I think that all the questions was answered. I think that we can move.
Yeah, I think maybe we'll wait for some questions.
Let's see. Okay, yes, we finished with the answers. One new question. Some detailed webinars are required for configuration.
That's a good point. We have made, or we started to do a short video section, kind of like expert videos, to also explain a little bit more in detail the configuration in Dixie, especially, and the workflow with the database also in the cloud. But then we will also try to upload this or to make this publicly. Yeah. Thanks for your active participation so far. All questions that we were unable to answer now during this webinar will be processed by us afterwards and made available to you by email. And we would like to take this opportunity to thank you once again for your interest and attention. And as a last note, maybe I would also like to point out our webinar series on our new automation platform, CCAM8. The first webinar in this series will take place actually the day after tomorrow already, on October the 12th. So if you haven't registered yet, please feel invited to do so or pass this information to interested colleagues. With these words, I would like to say goodbye from Bruno and me. Stay healthy and see you soon.